In the previous video, we have seen the weak duality lemmas. We are going to use the results from those lemmas to learn about a theorem that is called dual theorem. So let's start. The dual theorem says that suppose BV is an optimal basis for the primal. So in other words, we know which basic variables becomes the optimal basis for the primal. Then using that information, we may find the optimal solution for the dual. And then we simply need to compute CBVB inverse to obtain the optimal solution of the dual problem. And then we may confirm that the objective function value for primal and dual will be the same. Okay, so let me emphasize that this theorem says that the optimal solution for the dual is CBVB inverse. Okay, so if you have the primal problem and you know which variables becomes the basic variable, to obtain the optimal solution for the dual, again, you only need to compute CBVB inverse. So the proof for this theorem is that first we need to show that CBVB inverse is dual feasible, because to become an optimal solution, it needs to be feasible first. So we need to show that CBVB inverse is dual feasible. And then next, we need to show that the objective function value of the primal equals the objective function value of the dual. When we have shown that, then from the second lemma of the weak duality, we know that the solution that we have on hand for primal and the dual, they are optimal solutions. Let's go over the proof a little bit. So first, we would like to show that CBVB inverse is dual feasible. Let's start by assuming that we have a normal max as the primal and a normal mean as the dual. We convert the primal problem into standard form by adding slack variables. And now all the signs becomes equality. So in the primal problem, we have m constraints. It means that we have m basic variables. So we have m elements inside the CBVB inverse vector. And we just name the elements of CBVB inverse equals y1, y2, up to ym. And then in the primal table, if you remember, if you have a maximization problem and then you solve it with simplex, then the coefficient in row 0, they are all greater than or equals to 0 in the optimal table of the maximization, right? And then if you recall the formula to compute the coefficient in row 0, the formula is CBVB inverse AJ minus CJ. And then this is our CBVB inverse that we defined, and this is our AJ, and then we have CJ, which is the cost of the variable J. And then if we do the matrix multiplication, we have this result. And then we know that this must always be greater than or equals to 0, because in the maximization optimal table, the row 0, the coefficient of row 0 must be greater than or equals to 0. So for all variable j here, they are all must be greater than or equals to 0. Okay, so this is the requirement for the optimal table of the primal problem. Now, if we look at our dual problem, and then we notice the constraint, now we exactly see the same thing. You just need to move Cj to the other side, and then this is exactly dual constraint. What does this mean? This means that CBVB inverse is feasible in the dual problem. Well, there's one more thing actually to say that CBVB inverse is dual feasible. We need to make sure that these sign restrictions are satisfied. So we go back to our definition of CBVB inverse. We define it as y1, y2 up to ym. And then recall that in the optimal table of a maximization problem, In the row 0, CBVB inverse, they are the coefficients of the slack variables. And then because we assume that the table of the primal is already optimal, it means that all coefficients must be greater than or equals to 0, including the coefficients for the slack variables. So in other words, this y1, y2 up to ym, they are all must be greater than or equals to 0, which satisfies these sign restrictions. So we've completed the first step to show that CBVB inverse is dual feasible. In the first step, we showed that CBVB inverse is dual feasible. Now we are going to show that the primal objective function value equals the dual objective function value when our dual solution is CBVB inverse. So we define again CBVB inverse equals y1, y2 up to ym. And then if you recall the formula to construct the optimal simplex table, you know that to calculate the primal objective function, we use the formula CBVB inverse times small b. So this is our CBVB inverse, and then small b is the right-hand side of the primal problem. We have m constraints in the primal problem, so we have b1, b2 up to bm. So this is our primal objective function value. Let's take a look at the dual. If our dual solution is y1, y2, ym, in other words, if our dual solution is CBVB inverse, we see that the objective function value is b1, y1 plus b2, y2 up to bm, ym. So this is our objective function value for the dual when we have the dual solution y1, y2, ym, which is CBVB inverse, right? But then this thing here, if we just regroup the y's into row vector, we group the b's as the column vector, it is exactly the same with the objective function of the primal. So in other words, the objective function for the primal equals to the objective function of the dual when the dual solution equals the CBVB inverse. Once we have shown this from the lemma 2 in the weak duality, we can conclude that CBVB inverse is indeed the optimal solution for the dual. And then we have shown that the Z value for the optimal primal equals the W value for the optimal dual. Okay, so because CBVB inverse is the optimal solution for the dual, when we have obtained the optimal solution for the primal, imagine that we have obtained the optimal simplex table. We have actually obtained the optimal solution for the dual as well. Why? Because we may read the CBVB inverse from the optimal table for the primal. So for example, this is the Dakota problem, and this is the optimal table for the Dakota problem. Remember that we may read the CBVB inverse from the coefficients of the slack variables in the row 0 of the optimal table. Here we have 0 as 1, 10 as 2, 10 as 3. In other words, the optimal solution for the dual y1 equals 0, y2 equals 10, and y3 equals 10 as well. So this is the summary of how we may read the optimal dual solution from the optimal table if the primal is a maximization problem. Okay, so if the constraint is in the primal is less than or equal to, we just read the coefficient of the slack variable. If the original constraint in the primal is greater than or equal to, then the dual solution for yi is minus the coefficient of the excess. And then if the constraint in the primal is equality, then and then we solve the primal with big M, then here's how to get the optimal solution for the dual variable. And then remember, if you have the information of the parameters of the original problem, you can always directly compute CBVB inverse without solving the entire table. Okay, so you may just compute CBVB inverse to obtain the dual optimal solution. So it's the same. If you have already got the optimal table, then you may follow these steps. If you don't have the optimal table, but you know the basic variables in the optimal basis, then you just need to compute CBVB inverse directly. So whichever information is available to you, the point is you need to obtain CBVB inverse to get the optimal dual solution. Now, if the primal problem is a minimization problem, here are the ways to read the optimal table in order to obtain the dual solution. Okay, so again, you need to check the sign of the constraint in the primal if the primal is a minimization problem. Same as before, you can always directly compute CBVB inverse if you have the information about which variables become the basic variable in the optimal basis. But if you have the optimal table, then you may just follow these steps to obtain the optimal dual solution or to obtain the CBVB inverse. Okay, so given a primal problem, which is a maximization, and the optimal simplex table here, find the optimal solution for the dual. So first, let's create the dual of this problem. You don't always have to do this if you're already able to imagine that we have three constraints here, so we must have three dual variables. Then you don't really need to construct a dual if the question is only find the optimal dual solutions, right? You only need to know that you have y1, y2, and y3. Okay, so the given primal is maximization. So let's look at this summary here. And then to find the optimal solution for the dual, let's just look at the sign here. If it is less than or equal to, then we just read the coefficient of the slack variable. So y1 equals 51 over 23. The second constraint has the sign of greater than or equal to. So according to this summary here, we need to read the coefficient of the excess variable and then put a minus in front of it. So the optimal value for y2 equals minus 58 over 23. Now the third constraint is equality constraint. So we need to read the coefficient of A3. So this is the coefficient of A3, and what we do is we take that coefficient, but then we put minus m to that coefficient. So the result is 9 over 23. And then we can compute the W value, which is 565 over 23, and it is the same with the Z value here. What I meant is Z. Okay, so you've seen that we may use the optimal table of the primal to get the optimal dual solution. And it's quite easy, right? You just need to be careful with looking at what is the sign of the constraint in the primal, check the optimal table, and read the correct, whether it is slack, excess, or artificial variable, and be careful with the sign. Okay, so here's a question to check your understanding. Given a primal problem here, and this is the dual problem, and this is the optimal table for the primal. And then the statement says the optimal solution must have Z equals 6. So the optimal solution for the dual must have the value of Z equals 6. Is this statement true or false? I will give you the answer after the pause on the video. The answer is true, because if we are already given the information that this is the optimal table where W equals 6, then Z must equal 6 as well. Then if we would like to really show the value of each variable and compute the Z, we may do it. So for the first dual variable, let's see the first primal constraint, minimization. So this is how to read minimization table. So minimization, and the first constraint is greater than or equals to. It means we need to read the excess variable, the coefficient of this, and put a minus in front of it. So the value of x1 is minus 3, which is 3. The second dual variable comes from the second constraint, which is less than or equal to. And then here it says we just need to read the slack variable, the coefficient of the slack variable, which is 0, so x2 equals 0. And then the third constraint is equality. So here we need to read the constraint of a3 plus m. So this is the coefficient of a3 plus m, so it becomes minus 1. Now you plug in the value of 3 for x1, 0 for x2, and then minus 1 for x3, and then you will get the answer that the value of z is 6. Okay, so that's the end of this video, and in the next one we are going to talk about shadow prices, something that we have talked earlier in this chapter, but we are going to revisit that topic after we have seen this dual theorem. So see you on the next one. Thank you.